In this video, we will be going over Quantitative Proton NMR, or qHNMR, and its four methods to calculate the percent purity of your final product in your NMR sample. Before I begin, I have to give proper credit to the authors of this journal article where they discuss in detail the process of quantitative proton NMR, as well as give a step-by-step detailed guide to calculating percent purity for each of the four methods. These authors here have published the journal article, The Importance of Purity Evaluation and the Potential of Quantitative Proton NMR as a Purity Assay. I simply want to convert the information that was given in text form and turn it into a video format so that the methods are more accessible to a wider audience of individuals. Now, throughout this video, I will be showing multiple NMR spectrums, and if you need a closer look at them, you can go ahead and look at the supporting information in the article itself. It'll open up another PDF that shows a very detailed view of the spectrums. So the four quantitative proton NMR methods can be divided into two categories: the relative quantification and absolute quantification. Under the relative quantification category, there is one method called the 100% method. Under the absolute quantification category, there are three methods, and they are the internal calibration, external calibration, and ECIC method. The ECIC method is simply a combination of the internal and external calibration methods. One thing to note about the 100% method is that there is no required calibration step in order to calculate percent purity, whereas these three methods require a calibration step if you want to calculate the percent purity. One thing to note about the 100% method are some of its limitations. The 100% quantitative proton NMR method does not consider contributions from water. So if you ever see a water signal in your proton NMR spectrum, it is not considered in the final calculation for percent purity. This method also does not consider contributions from inorganic and organic chemicals that contain no or only exchangeable protons. So what this refers to are two things. One is residual solvent peaks, such as chloroform. Whenever you dissolve your sample into CdCl3, or deuterated chloroform, there is a small percentage of CHCl3 that's present in the bottle that you use to dissolve your final sample. The second thing it refers to are your OH and COOH peaks. This refers to this term, exchangeable protons. Remember that the protons for these functional groups can be acidic, and what can happen is that the proton can actually swap with a deuterium atom, and when that occurs, an OH and your COOH are sometimes not present in your NMR spectrum. However, if these two functional groups are present in your spectrum, you'll be able to easily indicate their chemical shifts because the signals will be wide, and this is due to the effect of hydrogen bonding. So remember, if you see an OH proton signal or a carboxylic acid proton appear in your proton NMR spectrum, under the 100% method, you do not count those signals in your final calculations. You simply ignore them. And lastly, the 100% proton NMR method does not consider sorbents such as silica gel or alumina. Silica gel or alumina can appear in your NMR spectrum if you were using column chromatography or PTLC, for instance, as a purification technique. So the main goal of the 100% method is to calculate the percent purity using this formula right here. Let's quickly go over the variables that are involved in this formula. The letter P stands for purity. The letter T stands for target analyte. I will be using the word analyte frequently throughout this video, and analyte is simply a fancy term to indicate target molecule. So whenever I say the word analyte, in your head, I want you to think target molecule. U stands for the number of impurities, and you can have multiple impurities appear in your NMR spectrum. You want to take account for each of those. So if you have 2 impurities, your U value is equal to 2. If you have 3 impurities, your U value is equal to 3, and so on and so forth. The N int sub t stands for the integral value normalized to 1 proton for your target analyte. We'll go over very shortly what it means to normalize your integral value. Your mw sub t is simply your molecular weight of your target analyte. And the n int sub u is your integral value normalized to 1 proton for your impurity. And remember, if you have multiple impurities, you need to calculate a normalized integral value for each of those impurities. Lastly is the mw sub u, and this is the molecular weight of your impurities. And again, if you have multiple impurities, you want to calculate the molecular weight for each impurity in your spectrum. Before moving forward, let's quickly go over integration. And I want to remind that integration is the measurement of peak areas on the NMR spectrum. It corresponds to the amount of energy absorbed or released by all nuclei participating in chemical shift during the nuclear spin flip process. It is used to determine the ratio of hydrogens that correspond to the signal. And this relates to the information that you can find in the journal article on pages 9223 and 9224, where the authors go into detail how integration is incorporated in the 100% method. So here we have our provided proton NMR spectrum, and our target analyte is this Q molecule right here. Our only impurity is this K molecule right here. So step 1 says to define all integrals and omit NMR solvent signals and water signals. Well, there are no water signals and there are no chloroform signals or any other solvent signals present in this spectrum, so we're good there. Next, we need to define all integrals, and we're also good here because at each signal right here, we have our integral value right next to it. Step 2 says to determine the number of protons in the target analyte that give rise to each of the integrated signals of the target analyte. So everywhere you see a Q, we need to determine the number of protons that give rise to the signal on the spectrum. And I'm going to tell you now that each time you see the letter Q, the signal that corresponds to the letter Q is made up of 1 proton. Step number 3 says to assign each of the integrals to all known chemical species in the sample, including the target analyte and all of the impurities detected in the sample. So we take each signal in the spectrum and we give it a letter corresponding to Q for our target analyte, or the letter K corresponding to our impurity. You'll notice that some of the signals actually contain a combination of both. We'll deal with those in the later steps. Step 4, determine the normalized integral of the target analyte and int sub t as follows. So there are 3 steps to determine our normalized integral. So step A says to identify the purest signal of the target analyte. Now this is arbitrary and it's up to you to decide what is the purest signal in your proton NMR spectrum. The authors decided to go with this signal right here with an integral value of 100. So next we need to determine how many protons give rise to this signal. Okay, so this doublet right here, remember that I said every time you see a signal with the symbol Q above it, this means that 1 proton gives rise to those Q signals. And lastly, the third step is to divide the integral value by the number of protons of that signal. So we know that this doublet represents 1 proton, and we also know that it has an integral value of 100. So we take 100 and set that equal to 1 proton. So now we have a relationship. An integral value of 100 is equal to 1 proton. And in order to find the normalized integral value, we need to divide the integral value by the number of protons of that signal so that we can find the integral value. So if we do that step, we get that our normalized integral value for our target analyte is equal to 100. Next, we need to determine how many impure signals are in the NMR spectrum. And remember that our only impurity is this K molecule. So we get that our U value is equal to 1. So we only have 1 impurity in the spectrum. Now that 1 impurity is scattered across in multiple signals. Step 6 says to locate the signals that contain only the impurity. Well, the signal at 8.0 ppm is the only signal that contains only the impurity. Step 7 says to determine the number of protons that give rise to the clean impurity signal. And the number of protons that give rise to the signal at 8.04 ppm is 2 protons. Step 8 says to locate the signals that contain both impurity and target analyte and determine how many protons give rise to the analyte portion of the signal. So there are 3 signals that contain a combination of the impurity and our target analyte, and they're located at 6.90 ppm, 6.40 ppm, and 6.19 ppm. And next we need to determine how many protons give rise to the analyte portion of the signal. So the analyte portion is our Q molecule, and we already know that this signal is worth 1 proton. So this signal is worth 1 proton, this signal is worth 1 proton, and this signal is worth 1 proton. Step 9 says to subdivide the integrals for these signals using the normalized integral value of the target analyte. So we know that each of these signals is a combination of our analyte and our impurity, but we need to figure out how much is the integral value for only the impurity, but we need to determine the integral value for the target analyte and our impurity. And we can do that by subdividing the integral using the relationship that we established earlier. We know that 1 proton in our target analyte is equal to an integral value of 100. So knowing that information, if we took this signal at 6.19 ppm, we can break it down by subtracting 100 from this integral value right here. So if we take 114.57 and we subtract 100, we get an answer 14.57. The analyte portion represents 1 proton, so we know that integral value is worth 100. So 100 is the integral value for Q, whereas 14.57, which we calculated previously, is the integral value for our impurity K. Now we'll have to repeat steps 6, 7, 8, and 9 until all integral values for the impurity and target analyte signals have been assigned. And I've gone ahead and done that and organized all that information into the table below. So just to go over the table, at 8.04 ppm, we know that it's only the impurity, so the integral value is 29.63. The signal at 6.90 is a combination of both the target analyte and our impurity. The integral value for only the target analyte is 100, and the integral value for the impurity K is 30.78. And all we did there is we took this integral value, 130.78, and we subtracted 100 from it, just as we did in this step right here. At 6.40 ppm, we know that this Q signal is worth 100. We know that this Q signal has an integral value of 100, so if we subtract that away from 114.40, we get that the integral value for the impurity K is 14.40. And lastly, at 6.19 ppm, we take 100, subtract it away from 114.57 to get that the integral value for K is 14.57. Step 10 says to determine the number of protons that give rise to each subintegral. So now that we've broken the combination signals into their proper subintegrals, we need to determine how many protons give rise to each of them. Well, let's start off at 8.04 ppm. We know that it's only the impure K signal, and we also know that 2 protons give rise to this signal. At 6.90 ppm, we know that the integral value of 100 is equal to 1 proton. The integral value of 30.78 is equal to 2 protons. At 6.40 ppm, once again, we know that an integral value of 100 is worth 1 proton. However, this signal right here represents 1 proton, so 14.40, that integral value is worth 1 proton. And lastly, at 6.19 ppm, we know that this Q signal has an integral value worth 100, and we know that 1 proton is equal to 100. However, the signal K has an integral value of 14.57, and this signal represents 1 proton from our impurity molecule. Step 11, determine the normalized integral for each subintegral. So let's take the signal at 6.19 ppm. We know that the integral value of the impure signal K is 14.57, and we also know that that signal is worth 1 proton, and we got that information from this table that we previously made. So if we take 14.57 divided by 1 proton, we get 14.57, and this value will be our normalized integral value, because remember that normalized normalized integral values are simply the integral values for one proton. We can go ahead and add that column. We can go ahead and add a new column to our table below, and we'll quickly go over this information. So at 8.04 ppm, we know that the integral value of k is worth 29.63, and we know that that signal is worth 2 protons. So if we take 29.63 divided by 2, we get 14.815 for our normalized integral value. If we move over to 6.90 ppm, we know that the integral value for k is 30.78, and we know that the protons that give rise to that signal is 2. So if we take 30.78 divided by 2, we get 15.39. The signal at 6.40 ppm, we know that the integral value for k is 14.40. We know that the number of protons that give rise to that signal k is 1. So if we take 14.40 divided by 1, we get a normalized integral value of 14.40. And lastly, 14.57 is the normalized integral value for k at 6.19 ppm, as we've previously calculated. Next, we're going to take those 4 normalized integrals, and we're going to calculate the normalized subintegral for each impurity by taking the average of the normalized integrals for the impure subintegrals. And remember, we only have one impurity in this NMR spectrum, and it's the only impurity in our NMR spectrum. If we had multiple impurities, you'd have to calculate a normalized subintegral for each of the impurities. We take the sum and divide that by 4, and we'll get an average of 14.79. This will be our normalized subintegral for our first impurity. Step 13 is to determine the molecular weights of the target analyte and impurity species. And lastly, we will need to repeat steps 5 through 13 if there is more than one impurity present in our proton NMR spectrum. So now we have all the necessary information needed to substitute in the values for those variables, and we would get a percent purity of 87.7%. But what if we wanted to find out how much of our final sample is only the impurity? Well, if we took 100% and we subtracted 87.7%, we would get an impurity value of 12.3%. 12.3% represents the amount in your final sample that is your impurity K. Now, if you've weighed your final product, you can take these percentages and multiply it by the mass of your final product. This would give you the pure mass of your final product, and you can also find out the mass of your impurity that's present in your final product. Next, let's move on to the internal calibrant method. Now, the goal of this method is to once again calculate the percent purity, but using this formula as provided. Now, we have some new variables that have been introduced, so let's go ahead and go over each of those. So N sub IC is the number of protons giving rise to the internal calibrant NMR signal. N sub T is the number of protons giving rise to the analyte NMR signal. The int IC is the integral value of the internal calibrant, and this is especially important. It's not normalized, so we're not going to do any normalization. The int sub T value is the integral value of the analyte. Once again, it will not be normalized as we did in the 100% method. So M sub S is the mass of sample amount added to the NMR tube. P sub I is the percent purity of the internal calibrant. Now, there are 5 ways of calculating the P sub I. The first way is to use the documented purity. So wherever you got your internal calibrant, let's say it's DMSO, you would look on the bottle and you would try to look for a number that tells you the purity of the solvent. A second way to find the P sub IC is determination by gravimetry or another primary analytical method. A third way is to determine the PIC through absolute qHNMR. A fourth way is determination by the qHNMR normalization method. This is also known as the 100% method. Now, if steps A through D are unfeasible, then we can just default this to a value of 100%. With that information out of the way, this here is our brand new proton NMR spectrum. And unlike the previous spectrum, we see some solvent signals appear. One thing to note about the internal calibrant method is that the authors recommend the use of DMSO D6 in order to dissolve your final sample in. Step 1 is to identify the purest signal of the target analyte and assign its integral as the integral of the target analyte int sub t, and determine the number of protons that give rise to this signal n sub t. Now, I want to also make note that if there are multiple signals, you need to identify the purest signal of the target analyte. Then you need to calculate the normalized integral values per proton equivalent by dividing each integral by the corresponding number of protons. Then you want to calculate the integral of the target analyte as the average of all normalized integrals. Then you set the total number of protons, n sub t, equal to 1. And the authors followed the latter. So there are 5 signals right here with an integral of 298.59, this signal with an integral of 199, this signal right here with an integral of 100, this signal with an integral of 98.70, and lastly, this signal right here with an integral of 99.13. So this signal is comprised of 3 protons, and you can determine that by looking at this integration line right here. Every time there's a step that indicates 1 proton, and in this case there are 3 protons. So in order to find the normalized integral, we would take 298.59 and divide it by 3. There are 2 protons in this integration line, so we take 199 and divide it by 2. There's only 1 proton present in this signal, so we take 100 divided by 1, and that's still 100. These 2 signals each contain 1 proton, so we leave it at that. These 3 would be already normalized. So we take the average of those normalized signals, divide it by 5, and we get a value of 99.37. This becomes our integral value for the target analyte. And remember, the previous step said for multiple signals that we need to set the number of protons for the target analyte equal to 1 if we're taking this average. So step 2 says to identify the purest signal of the internal calibrant and assign its integral as the integral of the internal calibrant and determine the number of protons that give rise to this signal. In this case, we're not going to be dealing with multiple signals, and the purest signal is this signal right here with a value of 132.68. We will be using DMSO2 as our internal calibrant, and the rationale for choosing DMSO2 is provided in the journal article as recommended by the authors. So our integral value for our internal calibrant is equal to 132.68, and the number of protons that give rise to this signal is 6. Step 3 says to determine the molecular weights of the target analyte and the internal calibrant. So I have listed down below the respective molecular weights of each. So step number 4 says to determine the masses of the NMR sample and internal calibrant. So the mass of the NMR sample, so this is the sample that gets put into the NMR probe, and we are given that that value in this scenario is 3.20 milligrams. And the mass of the internal calibrant, so it's pretty much like the mass of the solvent used to dissolve your sample, but we're also given that it is 0.228 milligrams. So one final step before we plug in all the values into our formula is the P sub IC. We are given that the purity of the internal calibrant is 99.4%. So with that in mind, we now have all the necessary values needed to substitute in for these variables. And when we plug in these values in our calculator, we'll get a percent purity of 70.8%. Next, let's move on to the external calibrant, or the EC method. Now, this is very similar to the internal calibrant method. There's slight variation in the formula right here that does not warrant me to give a full detailed list of the variables. So instead, what I've gone ahead and done here is showed the new changes. So wherever there is an EC, that stands for external calibrant, T stands for the target analyte, and S stands for the sample. If we want to acquire the purity of the external calibrant, there are 5 ways of doing so. One way is if you have a traceable reference material. So if you have a bottle, pretty much use the documented purity that that's labeled on your bottle for your solvent. The second method is determination by gravimetry or another primary analytical method. Third way is determination by absolute quantitative proton NMR. Fourth way is to use the 100% method. And finally, if those four previous steps are unfeasible, then we can set it to 100%. So this here is our brand new proton NMR spectrum. And you'll notice here that there are two spectrums. We have spectrum A and spectrum B. And just as the name of this method implies, we use an external calibrant in order to calibrate our integral signals. So this is very similar to the ECIC method, and what the authors have chosen here is to do the multiple signals variation of step 1. And there are 4 signals at this point, this, and this. So these 4 right here. So they all represent 1 proton. So there's no need to find the normalized integral, because if we take this value here divided by 1, that automatically gives us our normalized integral values. So if we add the integral values for each of the 4 signals divided by 4, we'll get the average of 230.25, and this average will be our integral value for our target analyte. And remember, we have to set the number of protons this time equal to 1. So step 2 says to identify the purest signal of the external calibrant and assign its integral as the integral of the external calibrant, and determine the number of protons that give rise to the signal. We will not be doing the multiple signals in this case. Instead, we will be taking the pure signal of the external calibrant. Now this is where it gets a little tricky. There are actually 2 external calibrants. The first one is caffeine, and our second external calibrant is DMSO2. So the purest signal for our caffeine is located around 3.85 ppm, and its integral value is 1109.38, and the number of protons that give rise to that signal is 3. The pure signal for DMSO2, its integral value is 2166.44, and the number of protons that give rise to that signal is 6. Step 3 says to determine the molecular weights of the target analyte and the external calibrant. So I have listed below the respective molecular weights for each, and you can take a look at them for yourself. And now we move on to step 4, which says determine the masses of the NMR sample and external calibrant. So we're given that the mass of the NMR sample is 6.66 milligrams. The mass of caffeine is 5.23 milligrams, and the mass of DMSO2 is 2.47 milligrams. We now have all the needed information required to substitute in for the variables of the equation, except for the purity of the external calibrant. Once again, the authors provide that the purity of the external calibrant is 98.7% for the caffeine and 99.4% for DMSO2. We need to respectively calculate the percent purity using caffeine as one of the external calibrants and DMSO2 as the other external calibrant. So this first calculation uses the values for caffeine. This second calculation uses the values for DMSO2. And we get that the percent purity using caffeine as our external calibrant is 98.6%. Using DMSO2 as our external calibrant, we get 99.1%. So what we do is we take an average of those two values, and we get that the purity is 98.8%. The final method is the ECIC method, and this is a combination of the internal and external calibrant methods. But it's a little bit different, where instead of first calculating the percent purity, we need to find the mass of the residual solvent. By now, most of these variables should look familiar to you. The only thing different is the subscript, so I'll quickly go over those. So wherever you see a R subscript, that stands for the residual solvent. Wherever you see the letter C, that stands for calibrant. There is a different variable used here. This is an M star sub R variable, and this stands for the residual protonated solvent in the analyte sample. So here we have our brand new spectrum, and similar to the external calibrant method, we have two of them. We have spectrum A and spectrum B. So step number 1 says in the qHNMR spectrum of the calibration sample, identify the purest signal of the calibrant, assign its integral as the integral of the calibrant, and determine the number of protons that give rise to the signal. And when there are multiple signals, you need to identify the purest signals of the calibrant, calculate the normalized integral values per proton equivalent by dividing each integral by the corresponding number of protons. Then you calculate the integral of the calibrant as the average of all normalized integrals, and finally set the total number of protons equal to 1. We will not be doing that. Instead, we will be taking a look at the purest signal, and the purest signal will appear right here around 3 ppm, and that value is 100 for its integral value. The number of protons that give rise to this signal is 6. Step 2 says to identify the signal of the residual protonated solvent, assign its integral as the integral of the residual solvent, and determine the number of protons that give rise to this signal. Well, the residual protonated solvent is located right here for DMSO D5. Now, normally the deuterated form of DMSO is DMSO D6, so that's dimethyl sulfoxide, and the methyl groups typically have methyl protons on it. The deuterated form would have deuterated atoms that are replacing the protons, so those would be 6 of them. Typically you would have 6 deuterium atoms. However, if you protonate that deuterated solvent by replacing one of the deuteriums with proton, then that becomes a residual protonated solvent because it becomes visible in the NMR spectrum because it now has a hydrogen on it, or a proton on it. So this is our protonated residual solvent, and this has an integral value of 141.33. And the number of protons that give rise to this signal, well, the others are deuterium atoms, and that's indicated by the D5. So that means 5 out of 6 will be deuterium atoms, meaning there's only 1 proton for this residual solvent peak. Step 3 says determine the molecular weights of the calibrant and the residual solvent. So I have listed below the respective molecular weights for each of those. And now we'll move on to step 4. Step 4 says assuming the purity of the residual solvent P sub R as 100%, determine the amount of residual protonated solvent in the calibration sample using the following equation. And we now have enough information to solve for M sub R. So when we solve for the mass of the residual protonated solvent in spectrum B, we get 4.50 milligrams of residual protonated solvent in spectrum B. If you're wondering where the 99.4% and the 0.605 came from, these were given values for this example. So step number 5 says taking into account the volumes of solvent used to prepare the samples, determine the amount of residual protonated solvent in the analyte sample. If both samples were prepared using the same volume of solvent, then M sub R star is equal to M sub R. So remember that we calculated our mass of the residual solvent to be 4.50 milligrams. And because both samples were prepared using the same volume of solvent, and we're given that information from the authors in the step-by-step guide, this means that M sub R star is also equal to 4.50 milligrams. So this means that 4.50 milligrams of residual protonated solvent is in our analyte spectrum, so spectrum A. However, if both samples were not prepared using the same volume, then you would have to go back to this formula right here and solve for your mass of the residual protonated solvent for your analyte spectrum right here. Step number 6 says, in the quantitative proton NMR spectrum of the analyte sample, identify the purest signal of the target analyte, assign its integral as the integral of the analyte, and determine the number of protons that give rise to the signal. If there are multiple signals, you need to identify the purest signals of the target analyte. Then you need to calculate the normalized integrals per proton equivalent by dividing each integral by the corresponding number of protons. Then you want to calculate the integral of the analyte as the average of all normalized integrals. Then you set the total number of protons equal to 1. So we will be doing the latter, and the signals that the authors have chosen are right here with the integral of 100, this signal with an integral of 201.06, and these signals right here for a integral value of 402.03. The signal at 100 is worth 1 proton. The signal with an integral value of 201.06 is worth 2 protons, so we take this divided by 2. This signal right here that's worth 402.03 is equal to 4 protons, so we take this integral value and divide it by 4. So there are 3 signals altogether, so we find the sum divided by 3 and we get an average of 100.35 as our integral value for the analyte. And we have to set the number of protons equal to 1 since we're dealing with multiple signals. Step number 7 says to identify the signal of the residual protonated solvent in the proton NMR spectrum of the analyte sample. Assign its integral as the integral of the residual solvent and determine the number of protons that give rise to the signal. So in our spectrum A right here, the residual protonated solvent is once again DMSO D5. And remember that typically there would be 6 deuterium atoms. However, one of the 6 has been swapped with a proton, and this now makes it visible on our NMR spectrum, and this is why it is our residual protonated solvent. So at 2.5 ppm, we have an integral value worth of 165.12. So we assign that as our integral for the residual solvent, and only 1 proton makes up the signal, and that's because one of the deuterium atoms has been swapped with only 1 proton. We now have all the necessary information to plug in for our variables in this equation right here. The only thing that we need to figure out now is the purity of our residual solvent, and we are given 100%. Also, we need to know the mass of our sample, and we're given that it's 10.67, and also this m star sub r, this value, remember that it's the same because we use the same volume to prepare both samples from the A spectrum and the B spectrum. When we plug in all these numbers, we'll get a purity of 78.4%. So that's all 4 methods to quantitative proton NMR. Through practice, these calculations become easier and easier and make a little bit more sense each time you do it. So I hope this video serves as a good reference point in guiding you towards solving quantitative proton NMR calculations. And once again, I want to give credit to the authors of the journal article right here for supplying the knowledge and information for quantitative proton NMR, as well as the 4 methods. This video would not have been possible without these authors listed here. And I want to thank you for watching this video, and I hope you found it helpful.